We came to the end of our, not the end in fact, but almost the end of this conference, and more specifically to the last talk, the last plenary talk. And this is a talk by REGINA BURACHIK from University of South Australia in Adelaide, Australia. And she will talk about conditions for zero duality gap in convex programming. So please, REGINA.
Thank you very much, Alfredo. I wanted to thank Alfredo for inviting me today. I'm very happy to be here in Rio and to be here at IMPA precisely because it's part of my history. I made my PhD with Alfredo here in this place, and I have a very strong attachment. So it's very nice for me to be here today. So this is a work on constraint qualifications for non-smooth convex optimization, and it's a joint work with Jonathan BORWEIN and LINGJIN. I will start by giving the framework and especially showing which is the model of optimization that we use for developing these constraint qualifications. And speaking about constraint qualifications, which is the main topic of this talk, I will also mention other typical constraint qualifications from the convex analysis, and especially the main idea of the talk is to emphasize the role of the use of epsilon subdifferentials in the development of optimality conditions for optimization. So in some sense, we see this is a talk on convex analysis, but it is also a talk on generalized monotonicity because it emphasizes the use of objects which are not monotone, which are the enlargements of a monotone operator in the development of optimality conditions for convex problems. So as one example of a constraint qualification for non-smooth optimization is what is known as closed epigraph condition, which is the second part, which I will mention in this talk. And then I will introduce a new closedness condition involving epsilon subdifferentials, which is a new condition for zero duality gap in convex optimization. And we will compare this with traditional standard optimality conditions from convex analysis, which is the classical interiority condition. And then we will present like a landscape of the interplay between all these conditions, and some of the relationships between these conditions I will show the results in this talk, and some consequences and also some open problems, because this is really a very interesting topic in the sense that some of the conditions, the connection between these optimality conditions is not known. It's an open problem. So the setting is a very general setting, but you can think of finite dimensions, you can think of Hilbert spaces. The reason for which we work in locally convex topological spaces is because we need separation properties. So we need separation, so any space where there is separation with linear functions. And suppose that what I will show in this slide, it has been shown in many other talks in this conference. These are some dual tools like the Fenchel conjugate and the epigraph. So I will pass this rather quickly because we have seen this. And now for a general proper lower semi-continuous convex function, we have, this will be the protagonist of the talk, the epsilon subdifferential, which is the set of all x star in the dual space, such that f of y minus f of x is bigger than x star y minus x minus epsilon. So this is a function of x and epsilon, and it gives this subset of the dual space. Now, the motivation of this talk is the constraint qualifications, as I said, constraint qualifications for convex optimization. So what is the model that we are going to use to understand the constraint qualification? So we will use a very symmetric kind of model. So suppose that you have a family, a finite family of locally convex topological spaces and a finite family of proper lower semi-continuous function, and you consider this minimization of the sum of each of the function in each of the product space, in each of the spaces. So in x1 you have f1 of x1 plus f2 of x2, etc., and you take the sum of these functions and you want to minimize it. Of course, if you want to minimize, you have to add a constraint to make these functions really related to each other. So the constraints that you use is a closed subspace. I say here a closed subspace. In infinite dimensions, a subspace might not be closed. So, but in finite dimensions, you just take a subspace. This model is very similar to the monotropic programming optimization problem, in which you have a sum of separable convex functions, and you have a constraint which is a subspace. I will show now that the fact that we assume that the functions go to plus infinity implies that this model is general and it includes any convex optimization problem. And the dual of this problem is really very symmetric, is exactly symmetric, and this is the reason for which we have chosen this model to analyze the convex problem. There is this writer, Argentinian writer, Jorge Luis Borges, who was saying that reality likes symmetries. And it's very interesting. In mathematics cannot be different. So we consider the primal problem the minimization of a sum of convex functions subject to a subspace, and the dual will be the maximization of a sum of concave functions. Each of these concave functions is the conjugate function of each of the terms in the original objective function, and the constraint is precisely the orthogonal to the subspace in the primal space. So there is, as you see, there is perfect symmetry between the primal and the dual problem. And once you have this scheme, I just want to show to you very quickly what I said to you before, that every convex problem can be modeled in this way, because if you have a convex function and a closed convex set, the general convex optimization problem of minimizing this function subject to this convex set is perfectly written as the minimization of a sum of a function in the space X plus the indicator function in the space X as well of the subset C, and the primal variables are in the product space X times X. So you can model any convex optimization problem in the way I showed you before. So there is no information lost by using this model. This model of sum of convex functions subject to subspaces is also used in many applications. So there are some papers by Bertsekas in which he uses this for approximating convex functions by using polyhedral functions. Now let's go to the main thing that motivated this work. Bertsekas published in 2010 a constraint qualification for this model for monotropic programming problems, in which he was saying that if a certain set is closed, then you have strong duality gap for this kind of convex optimization problem. And he has a beautiful proof of that fact, and in the proof he uses the fact that this set here is closed. And there is no real connection between the closedness of this set and the zero duality gap in principle, because he uses the closedness of this set in the proof, because he proves it by developing a descent direction, and for finding a search direction of that descent direction, he needs the closedness of this set to be able to project, get a point in the projected set, and he has to be able to say that the projection belongs to the set. So it's some kind of, he needs it in the proof. So he puts it and he proves the zero duality gap in that way, in finite dimensions. In the same year, Boch proves the same result in general spaces. Bertsekas proves it in finite dimensions. Boch extended to convex topological spaces and locally convex topological spaces, but he uses a totally different proof, which makes you think that this closedness of this set may have nothing to do with the descent direction that he uses in the proof, but it's something that it's inherent to the problem. It's something that is really connected with the property of zero duality gap and not with the descent direction. So this is the motivation of this talk, to understand better this property. Now, just I will try to express the thing in the green box. I will write it as it is in the yellow box, because you know this term here is nothing but an epsilon subdifferential. The orthogonal to the subspace is the epsilon subdifferential of the indicator function of the subspace S. So when you look at it from that point of view, you see that what is there in the green box is nothing but a sum of epsilon subdifferentials. Why? Because this product of epsilon subdifferentials of each of the function terms can be expressed as an epsilon subdifferential of functions defined in the whole space in such a way that this function f1 of x is simply, instead of f1 of x, is f1 of x1. So instead of defining as domain x1, you can take the domain, the whole product of all the spaces, but it is exactly equal to f1 of x1. So it only depends on all the other, it only depends on the variable x1, and it does not depend on the other variables. Therefore, the subdifferential will have, the epsilon subdifferential will be non-zero in the coordinate 1, let's say, and 0 in all the other coordinates. So you can express the epsilon subdifferentials as the sum of epsilon subdifferentials of functions defined in the whole space. So in the end, what you have there is you have to request the closedness of the sum of epsilon subdifferentials defined in the whole space. So this is the kind of constraint qualification we are looking at, and we want to understand the exact connection of this constraint qualification with the zero duality gap. So this will be our first step. And the second step will be to understand which are the related conditions to this condition in the green box. Which conditions imply the green box and which conditions are implied by the green box. In that way, we will understand whether our problem satisfies the constraint qualification or not. Okay, so let's go ahead. I said to you I wanted to speak about this closed epigraph condition because we were all thinking that there is a connection between the Bertsekas constraint qualification, which was the condition in the yellow box, and this closed epigraph condition. So the closed epigraph condition is a condition that is requested for the subdifferential of the sum to be equal to the sum of the subdifferentials, which is an important condition in terms of characterizing solutions of optimization problems. So this condition is a closedness type of condition, and we were thinking that there must be a connection between this condition and the condition of the sum of the epsilon subdifferentials being closed. And we've been trying to prove it, and in fact what we proved is more on the negative direction. Together with my PhD student Saba Majid, we proved that it is a fact that the closed epigraph condition is not stronger than Bertsekas constraint qualification. And now, before we go a little bit ahead, we want to mention a condition, an expression for zero duality gap. And for that, we need to recall a tool that has appeared many times in this conference, which is the infimal convolution. The infimal convolution of a finite family of functions is the infimum of all possible sums of functions at points such that the sum of those points gives us the point z that we have here, that we have in the domain of the infimal convolution. So we take a z, we take all the possible decompositions, additive decompositions of z, we take the functions on those points, and we take the infimum. And that infimum is the value of the infimal convolution. And the infimal convolution is said to be exact when this infimum is attained. So exactness is one thing, and the existence of the infimum, the finiteness of the infimum, is another. So the zero duality gap, in fact, and this has been shown before in this conference, the zero duality gap is nothing but asking the infimal convolution at zero, the infimal convolution of the conjugate functions at zero, be equal to the conjugate of the sum of the functions at zero. So zero duality gap between primal and dual is nothing but the equality of two functions at zero. One of those functions, a lower semi-continuous function. So this function here on the left is a lower semi-continuous function, but we are not requesting the infimal convolution to be lower semi-continuous, but we are requesting to be equal to lower semi-continuous function at zero. And this is exactly the zero duality gap. So it is clear that one condition that will clearly imply zero duality gap is the equality of those two functions everywhere. So if you require those two functions to be equal everywhere in the space, then in particular they will coincide at zero, and you will have zero duality gap. So what we will see is a connection between Bertsekas constraint qualification of the sum of the epsilon subdifferentials being closed, a connection between that condition and the equality between these two functions. And this condition, just because it's very difficult to say the equality between these two functions, we can call this the red tree condition. The red tree condition. So this condition will be called the red tree condition. And this is the new condition we are presenting here in this talk. And because it's very difficult to say all the elements in this box, we will call this condition the red bird condition. And the red bird condition says the following. It's related with the closedness of the sums of the epsilon subdifferential, but it's not exactly the same. It's not exactly the same. You take the sum of the epsilon subdifferentials. That is in principle not a closed set. So what do? You take the weak star closure of that set. And then you know that in principle will not be equal to your original set, which is below this line. But it might be equal to something which is very similar, which is the sum of not exactly the epsilon subdifferentials, but the sum of k times epsilon subdifferential for some constant k positive. That constant k ideally will be larger than 1, larger than or equal to 1. So k equal 1 has a critical role in this condition, but doesn't matter here. That's not relevant. What is relevant is that this is a constraint qualification, and this will be called the red bird condition. Now, it is clear that if you have Bertsekas constraint qualification, then the red bird condition is true for capital K equal to 1. because your original sum is already closed. So you can take capital K equal to 1, and therefore we want to show, what we were going to show now is that the three condition, the equality between those two functions and the red bird condition are equivalent. Therefore, that's why and that's how you obtain zero duality gap from the Bertsekas constraint qualification. Okay, before we do that, I wanted to remind another constraint qualification which is very standard in the literature, which is known as interiority condition or interior point condition. So there are many expressions for the interiority conditions. We will use the condition that the domain of one of the functions intersects the interior of the domains of the remaining functions. So we will use this expression. And now we show this very messy thing. I couldn't do it in a better way. But we have here the interiority conditions. So the interiority condition represents the most strict condition. And on the other side, we have the tree condition. The tree condition is the equality between the functions and is the less restrictive condition. How do we go about this graph? So the interiority condition implies the closed epigraph condition. Closed epigraph condition is less restrictive than the interiority condition. This has been proved by Salinescu, by Boch and Vanca. In fact, Salinescu didn't prove it directly, but it can be deduced from Salinescu's book material. And then Boch and Vanca made it more specific in 2006. And the interiority condition implies Bertsekas constraint qualification. And this is something that we are going to prove in this talk. And the connection between the closed epigraph condition and Bertsekas constraint qualification. I have mentioned one of the arrows is not true, and the other arrow is a non-pair problem. So we really don't know what happened in the other direction. We tried, but we couldn't, and I would really be very interested in knowing if it happens that that the closed epigraph condition implies or not Bertsekas constraint qualification, or maybe they are unrelated. We don't know that. I don't think they are unrelated, but maybe it's true. And then, as we saw, we just saw that Bertsekas constraint qualification implies the bird. And another thing that we are going to see today is that the closed epigraph condition is equivalent to the tree condition plus exactness. So now we see why the closed epigraph condition is much stronger than zero duality gap, because it also requires exactness of the infimal convolution. Not only the equality of the functions, but also the exactness of the infimal convolution. And as I mentioned before, the tree and the bird are equivalent. They are equivalent conditions, as it was intuitive to think. The tree and the bird can only be equivalent. And then the closed epigraph condition is more restrictive than the bird. And also the bird does not imply the closed epigraph condition, but that's a result of the whole figure. That doesn't need to be proved. Anyway, I just wanted to remind what are the bird and the tree. For those who are not paying enough attention, the tree is the equality between the functions, and the bird is this, you take the sum of the epsilon subdifferential, take the closure, the weak star closure, and then you assume that the weak star closure is inside something of the same kind. Okay, so now in convex analysis, there are a lot of nice formulas that have no kind of assumption on the data, only convexity. So this is one example. So this formula can be found in Salinescu's book, and it says that the epsilon subdifferential of the sum can be expressed as the sum of the epsilon subdifferentials in this way, as the intersection for every eta positive of the union of all the epsilon subdifferentials of the guys which are a little bit bigger than epsilon. And then when that perturbation eta is 10 to 0, you take the intersection, and you get the epsilon subdifferential of the sum. And the only annoying thing of this formula, the annoying part of this formula, what is that closure there that nobody knows what to do with that closure. Everybody hates that. But it's a very nice formula, and you would like to get rid of that closure. So what we have is that under some technical assumptions, and the assumptions are the requirement that the function coincides with the closure of the function on the intersection of the domains of the closure. So you take the domain of the closure of the function, you take the intersection of all of them, and then you request that every single function coincides with its closure on that set. That's the assumption that we make, and of course the intersection of the domains is not empty. And then effectively you are able to prove, and this proof is not easy, but it uses very strongly Salinescu's formula, that the tree is equivalent to the bird, and this is equivalent to the fact that the infimal convolution is lower semi-continuous. So the infimal convolution is lower semi-continuous, and that is a constraint qualification in itself. A weak one, but it's a constraint qualification. And as a consequence of that, you can simplify Salinescu's formula. You can get rid, if you have this assumption, you can get rid of that closure, weak star closure. In fact, it's equivalent. So it makes the formula neater to have that constraint qualification. So in fact, in this way, you have a simpler expression for the epsilon subdifferential of the sum. Okay, so this is something we have mentioned before, but this is the connection between these. This is showing the proof of two of the arrows that I have shown in the previous slide. So this theorem implies two of the arrows, implies the equivalence between the tree and the bird, and implies the fact that bird secas is more restrictive than the bird. Okay, so now let's go to the other arrow that I was mentioning before, the arrow that implies that says that closed epigraph condition is equivalent to the tree plus the exactness of the infimal convolution. This is a result that I thought that it was published, because the closed epigraph condition has around 10 years already. I thought it was published, but we couldn't find it, so we proved it again. I don't know why. So this is I won't go on the proof now because we don't have time. But this is a fact, and it's important to understand the connection between the exactness, the tree condition, and the closed epigraph condition. Okay, so another important comment, and it's this another arrow of the general landscape I showed to you, is when we have an interiority condition, what can we say? So it is well known that if you have a point in the interior of the domain of the subdifferential and of the epsilon subdifferential, then the epsilon subdifferential is weak star compact. And therefore, if you take the epsilon subdifferential and you sum them with other epsilon subdifferential, they will all be compact sets, and therefore the sum will be compact and therefore closed. However, in this result is a little bit stronger than that. It tells you that whenever you have the interiority condition, no matter where you are computing your epsilon subdifferential, not necessarily in an interior point, the sum of the epsilon subdifferentials will always be weak star closed. Because these sets that you have here, in principle, they are not compact if the point is not in the interior. But in fact, you can prove something stronger. If you have the interiority condition, you can prove that for every point which is in the intersection of the domain, the sum of the epsilon subdifferentials is closed. Okay, so another thing about the implications of this for sublinear functions. We know that for sublinear functions, the closed epigraph condition is equivalent to the subdifferential sum formula. Is equivalent for sublinear functions. So in some sense, this may make you think that, okay, then we cannot find anything which is less restrictive than the closed epigraph condition, because if for some family of functions you get the formula as equivalent to that condition, maybe why would you look for a less restrictive condition? Well, then in spite of that, we wanted to study what happens for sublinear functions with this less restrictive constraint qualification of the bird or the tree. And then what happens is that if you have sublinear functions, all these constraint qualifications collapse somehow. So what you obtain is that, under the same technical assumptions as before, you have, of course, the equivalence between the tree and the bird. You have that the infimal convolution is weakly lower semi-continuous, and you have also the nice version of Salinescu's formula, but you also have that this is equivalent to the subdifferentials of the functions at zero, the sum of them being weak star closed. It's equivalent to the closed epigraph condition, and it's equivalent to, it's equivalent to the equality of these two functions, and this is contained in the tree condition, and it's equivalent to the subdifferential sum formula. So in this case, all these constraint qualifications collapse into one. They are indistinguishable for sublinear functions. Okay, so we like formulas very much, and we like to take out those closures. And then we took this Hilliard-Turruti-Phelps formula from 1993 that says that the subdifferential of the sum of functions can be expressed as the sum of the epsilon subdifferentials as the intersection of the epsilon subdifferentials, and then you sum them up, and then you take the closure. And this is Hilliard-Turruti's formula. So again, there is this closure here that you would like to get rid of. And what happens is that, and this is not difficult to show, that if you have the closed epigraph condition, you get rid of this, of the closure, and you can use the closed epigraph condition to show the subdifferential sum formula here. So this is known. So the question is, what happens if you have the bird condition? If you have the bird condition or the tree condition, what happens with this Hilliard-Turruti-Phelps formula? Of course, you won't get such a nice, neat result as this one, but you may get something interesting anyway. So in this case, what happens with the formula is that you get rid of the closure. So the bird condition helps you to simplify the Hilliard-Turruti-Phelps formula in this case. Now, so I am finishing now. I will finish in some minutes. I would like to finish with some open questions related with this. So the first open question is the one in the interplay between the different constraint qualifications. So what is the relationship between, what is the exact relationship between the closed epigraph condition and Bertsekas constraint qualification? And especially to understand if it's really strictly more restrictive than the bird condition. And another question is, what happens if we consider other kinds of objective functions? So if instead of considering the sum of convex functions, we consider f plus g composed with a linear operator, capital A. So when you have this kind of expression, can you have different constraint qualifications? And another important thing is that this constraint qualification is based on epsilon subdifferentials. And you know that epsilon subdifferential is simply some particular enlargement of the subdifferential. What happens if you choose another kind of enlargement of the subdifferential? Can you get some new information? Can you get some nicer properties? Or maybe you cannot. So if you take this other set, which is this kind of enlargement, which is the set of V in X star, such that, and here you would get V minus U, X minus Y is bigger than minus epsilon for every Y and for every U in the subdifferential of F of Y. So this is larger, so this set in general contains the epsilon subdifferential, and it may be different. So can we express these constraint qualifications in terms of that enlargement? This is a bigger enlargement, and this enlargement has different properties, and in particular some properties which are better than the epsilon subdifferential. Can we get new results, and can we use these elements to generate new constraint qualifications? And finally, what happens with conditions for variational inequalities? Can we think of constraint qualifications for variational inequalities? Because if you look at these optimality conditions, they are all based on enlargements. They are not based on the precise functions. So you can get rid of the functions. Think just of the enlargements and try to propose problems associated with the operators themselves, with the subdifferentials. And if you have just maximal monotone operators and a variational inequality in terms of a sum of maximal monotone operators, can we use these enlargements to define constraint qualifications for these problems? And of course, that would mean that we have to also have a scheme to develop the dual problem as well, and to understand this duality better. Thank you.
Okay. Questions, comments? Claudia.
Dale el micrófono.
So, yes, constraint qualifications are very important, and you can be very general. However, it is important to be able to check them, right? So I think in number 3, the proposal that you are, what you are proposing to analyze this composite function, it would be interesting also to particularize the function G to a positively homogeneous convex function, because there you will have all these subdifferentials, epsilon subdifferentials that are the subdifferentials and that are collapsed at 0, and you might get rid of many bars. You see, and it's general, still general enough composite functions where the outside operator, the convex function, is positively homogeneous. So sublinear.
You mean sublinear? Okay.
It's the same.
Yes. Yeah. Yes, that would be very interesting. Yes.
And another generalization that might be interesting is to consider functions that are lower C1, because lower C1 functions have this property of epsilon. They are epsilon submonotone.
These ones?
Like your enlargement there.
Yes.
Lower C1 functions, Spinger, I think, proved they satisfy this inequality. And so it can be interesting. They are non-convex, but a little bit convex. And then you can maybe...
But Claudia, every function satisfies this inclusion. You mean
No, I'm not saying the inclusion. No, I'm saying that the subdifferential of a lower C1 function satisfies the inequality with the minus epsilon on the right.
Ah, okay.
You see? So
okay.
you are as if in your enlargement already with the subdifferential of a lower C1 function.
Okay, thank you.
Okay, Regina, indeed, very broad territory has been covered in your talk, and I have 2 specific questions. One question about finite dimensionality. I believe that you have some simplification of your results in finite dimension. About interiority condition, you probably don't need interiority. And also, what about this bars? Could you avoid some bars in finite dimensions?
I don't think so in finite dimensions. No, the interiority condition is really needed.
Not relative interiority?
Sorry?
Not relative interiority?
Maybe yes,
Yes,
you're
that's
right.
what I mean,
Yes,
right,
you're
yeah.
absolutely right. Yes, in finite dimensions you can replace the interior by the relative interior. Yes,
And
that's
what
true.
about these bars? Any case when you can avoid this closure?
In finite dimensions.
Weak. You can
No,
take
weak
the
for
W,
sure.
but the bar-
No, no,
It
but
might be.
still.
It might be. No, I think. Well, I have to look at it.
Yeah, of course, no, weak,
Yes.
not a question, but just closure. Do you have some closure automatic or under some middle condition?
I think that no. I think you are right. And in fact, I wanted to add here. In this, we have this in the archive. We have simplifications for the case of polyhedral functions. I didn't add this here because I thought I wouldn't have time, but we have for polyhedral functions and we have for finite dimensions, yes.
Wonderful.
There
And
is
then
simplification.
the last question. Did you think about bilevel problems?
No.
No, I'm sorry, bilevel, difference of convex. I'm sorry. I
No,
thought
we
about
didn't think
difference
of that, but there are some formulas for difference. We didn't think of that.
It would be very nice indeed, because this actually has application to bilevel programming for just a difference of convex. And in this case, there are some kind of interplay between these two functions. And we can talk maybe a little bit more.
Okay.
Yeah.
Okay.
Thank you.
Thank you.
Any other? Okay. Oh, we have a lot. Okay.
You said that in some occasions you can eliminate the bar when the function is polyhedral. Is it also be locally polyhedral? That means that if you consider the convex consideration by the set minus the
We didn't consider that condition. We just used for polyhedrality, but it would be interesting to look at that. Yes, maybe simplified would be nice.
Okay. Wait a minute. I will bring you the.
So my question is the following. This kind of objective functions are very important in optimal control theory when f and g are certain norms in certain Sobolev spaces. This is the square of the norms. And A is a solution operator of a partial differential equation. This is the link actually between the control and the state. And if A is linear, the situation is not easy but easier than when the situation is nonlinear. So my question is, what do you think, is it hopeless to examine this question when A is not a linear operator but a monotone one? Monotone and hemi-continuous and so on.
I think
You lose convexity.
Yes.
you lose
Yes.
as
Convexity of the sum.
if you
Yes.
lose convexity, you cannot use this. But
okay.
the idea of putting this number 3 is because it may generate a different kind of optimality condition. So you can express, as in the same way as I express the bird condition, you can get a bird condition for this expression. And that may be used in your case. But you need convexity,
Yes, this
as
is why
far
I
as
asked
I
it.
know, you need convexity of both F and G.
And on the sum.
Yeah, yeah.
Yes, well,
No,
if
because he was proposing to make A non-linear.
yes,
Yeah.
well,
A is not linear even if F and G are convex, but the sum is not, and so this breaks.
Actually, you don't
Yeah.
know too much about the sum in this case, though. So what can you do? So nothing?
well, maybe this analysis is for the convex case. So this analysis is more for the convex case. Maybe you can do something for the non-convex case, but I don't know.
Maybe you can use the
Michelle,
FW star.
sorry, there was somebody.
Maybe.
Just an historical comment. Informal convolution plays a central role in your talk, and it's a beautiful object in convex analysis. It has been discovered by Fenchel, by the way, the first one. But do you know who named for the first time informal convolution?
No.
It's Jean-Jacques Moreau in 1963, in Compte rendu à l'Académie des Sciences. And since it's a year, unfortunately he died this year, it's good to remind.
To remind. Okay, thank you.
Okay.
Thank you.
Any other question or comment? Well then, we thank again Regina. And now, I thank all of you for coming. I think that this has been a great conference, perhaps not so big as some previous editions.